Hello everyone, I'm Ümit Alkuş. In this video, we will solve one problem in chapter 11. Two blocks of masses M1 as 1.5 kilograms and M2 as 4 kilograms are connected by a string that passes over a frictionless pulley whose radius is capital R 7 centimeters and whose rotational inertia is I as 0.38 kilogram meters squared. Horizontal surface has coefficient of kinetic friction μk as 0.4, but the inclined plane with theta equals 35 degrees is frictionless. The system is released from rest. A. Draw the free body diagram of the blocks and the pulley. First of all, let us draw the free body diagram of the blocks. The appropriate coordinate systems are as follows. We represent the blocks by a big dot. Next, we draw all the forces acting on the bodies. The first force is the gravitational force. For M2, it is convenient to decompose M2g onto x and y axis. The tensional force due to the string on M1 is T1, which is to the right. The tensional force due to the same string on M2 is T2, which is an upward force along the surface. Because there is a contact between M1 and the horizontal surface, the normal force, which is perpendicular to the surface, is drawn as the following. Similarly, since there is a contact between M2 and the inclined surface, the normal force is drawn perpendicular to the surface as the following. Because there is a friction between M1 and the horizontal surface, the kinetic frictional force acting on mass M1 is drawn to the left, because the motion is to the right. As the final step to draw the free body diagram of the blocks, we draw the acceleration vectors like this. Okay, let us draw the free body diagram of the pulley. Because there is a rotation, we represent the pulley as it is, not by a dot. The rotation of the pulley is only due to the tensional forces on the strings, and they are depicted as follows. And because of the whole motion, the angular acceleration denoted by alpha is drawn like this. Okay, these are the free body diagram of the blocks and the pulley. B. Find the linear translational acceleration of the blocks. Equation of motion for M1 is F net equals M1 times A by the Newton's second law. Now we write the equation of motion along the x-axis. If we take the direction of the acceleration vector as positive, the net force along the x-axis becomes T1 minus Fk. Since Fk is μk times n1, the equation of motion along the x-axis becomes T1 minus μk times n1 equals m1 times A. For the equation of motion along the y-axis, since we know that there is no motion along this line, that is, acceleration is 0, then we write n1 minus m1g equals 0. Therefore, the normal force n1 becomes m1 times g. If we put this expression into the above equation, we obtain this equation. The equation of motion for M2 is F net equals M2 times A. To write the equation of motion along the x-axis, we choose the direction of the acceleration vector to be positive. Therefore, the net force along the x-axis becomes m2g sine theta minus t2, which is equal to m2a by the Newton's second law. Because there is no motion along the y-axis, the net force N2 minus m2g cosine theta becomes 0. From this, we obtain an expression for N2 as m2g cosine theta. Equation of motion for the pulley is found by the formula net torque equals I times alpha, where I is the rotational inertia and alpha is the angular acceleration of the pulley. This equation is also known as the Newton's second law for rotational motion. Torque has the formula R cross F, and its magnitude is found by the formula R times F times sine phi, where phi is the angle between R and F. Therefore, torque due to T1 is found by the formula R1 times T1 times sine phi 1. Here, phi 1 is 90 degrees, so sine 90 degrees is 1, and R1 is the radius of the pulley, which is capital R. So, we obtain the torque due to T1 as capital R times T1. The direction of the torque is found by the right-hand rule, so it is in the positive z direction. Similarly, the torque due to tensional force T2 is found by the formula capital R times T2. And by the right-hand rule, the direction of the torque is negative k hat. So we write negative R times T2 times k hat. The equation of the rotational motion by the help of the Newton's second law is net torque equals I times alpha. If we take the direction of the acceleration vector to be positive, then the net torque becomes tau 2 minus tau 1, which is equal to I times alpha. Tau 2 is R times T2, tau 1 is R times T1. Therefore, we obtain RT2 minus RT1 equals I alpha. Here, for the pulley to rotate without skidding, we have the formula for the linear acceleration as A equals R times alpha. From this, we obtain angular acceleration alpha as A over R. So, I times alpha becomes I times A over R. The left-hand side of the equation becomes R times T2 minus T1. If we divide both sides by R, we obtain T2 minus T1 as I times A over R squared. Okay, if we add these three equations side by side, T1s are cancelled, also T2s are cancelled, then we are remained with m2g sine theta minus mu k m1g on the left hand side. And right hand side becomes, the left hand side can be written as g times m2 sine theta minus mu k m1. And right hand side can be written as, from this equation, we obtain an expression for the linear acceleration A as, we put the numerical values into the corresponding places. So, the linear acceleration of the blocks is obtained as 0.19993 meters per second squared. Or in 3 digits, it is approximately 0.2 meters per second squared. C. Find the angular acceleration of the pulley. There's a relation between the linear and the angular accelerations as follows. A equals r times alpha, from which we obtain alpha as a over r. We put the numerical values into this formula. Then the angular acceleration of the pulley is calculated to be approximately 2.86 radians per second squared. The unit is radians per second squared because angular acceleration is the first time derivative of the angular speed, and it is second time derivative of the angular displacement, which is in radians. D. Find the tensions T1 and T2. From equation 1 in part B, we have T1 as m1 times mu k times g plus a. With the numerical values, we obtain tension T1 as 6.1799 newtons, or approximately 6.18 newtons. From equation 3, we obtain T2 as I times a over r squared plus T1. Now substitute the numerical values into this formula. Therefore, we obtain approximately 21.7 newtons. Okay, this is the end of the discussion of this problem. Thank you for your attention. See you in the next video.